Thank you very much. So today I'd like to share a little bit about how Honeycomb has managed to keep our service up in the face of escalating demands in terms of both number of users requesting our services, as well as feature sprawl and all of those lovely and wonderful things that come with software development. So the field of observability is evolving really quickly. In particular, what we've seen is that people are starting to really understand this idea that we need to be able to debug and interrogate our software systems in order to be able to tame and manage complexity in the field. And not only that, OpenTelemetry has gone from a niche thing 3 years ago to being something that is now one of the top CNCF projects. We are now the second most popular CNCF project with the highest commit velocity beyond Kubernetes. So what this boils down to is that practitioners in the field require velocity, reliability, and scalability, and that these are things that we can help them with. But how did we manage to do this with only about 50 engineers? And how did we manage to keep up with companies that were shipping features and software with 500 engineers that were competing with us? So part of how we do this is that we make sure that we're always deploying all the time. Not deploying once a week or even 4 times a week. We deploy up to 14 times per day, every single day of the week. And when I mentioned earlier about traffic increasing, traffic has really, really gone up. Since the last time that I was here for YOW in 2019, we've seen a growth of 10x, both in terms of the number of average data points ingested per second, going from about 200,000 query points ingested per second to over 2 million data points ingested per second. We're also seeing the number of queries from our users increase by a factor of 10, because it turns out that during the pandemic, everything moved online, and people depend upon their online services to conduct their day-to-day activities. So how do we manage to ship reliably and manage everything in the face of chaos? Well, first of all, we have to have a definition of what reliability is for us. So we have to measure what expected level of reliability our customers want from us. And then we have to plan. We have to think about what might jeopardize our reliability to our customers, and how can we actually verify that our system has the safety properties that we're looking for. And then finally, we actually go ahead and make sure that we are paying down our technical debt backlog rather than have it grow and grow and grow until things fall over. So let's talk first about what our definition of reliability is for an observability provider like Honeycomb. So this goes back to the idea of service level objectives and measuring what too broken is from the perspective of our customers. So fortunately, I don't have to explain this in a lot of detail because there's loads of reading material. But in short, a service level objective is this core concept of measuring critical user journeys and determining what percentage of them need to be completed successfully in order for user expectations to be met overall. And the core idea is essentially that you cannot achieve 100% uptime, so we shouldn't try to achieve 100%. We should try to achieve something that's more realistic that meets our customer needs. And SLOs are really this opportunity for us to negotiate with our customers, with our product management team, to really get down this idea of, OK, reliability is a product feature. How do we actually ship to that rather than to a goal that's too high or too low? And it turns out the last time that I was here in Brisbane, that's exactly what I talked about. So when we have SLOs, SLOs enable us to really focus only on things that are customer impacting and not have the sea of noisy alerts. It's really fantastic. So what does it look like for us as Honeycomb? Well, there's a lot of moving pieces in this, but essentially, Honeycomb users send us something like 2 million data points per second at peak. And our job is to reliably serialize them onto disk so that we can index them and retrieve them on demand within seconds so that our customers can understand what's happening in their software systems when they need it the most. When your site is down, we need to be there for you. You need to feel that you can confidently rely upon us to help you debug your problems. So under the hood, we're using a lot of cloud computing technologies like serverless, like cloud object storage. These are all things that work in service of that. But we are fundamentally the owners of that ingest pipeline, and we have to make sure that it works correctly. So in terms of user flows, what this boils down is 3 things. First of all, that if you want a snapshot of what's happening in your production system, we need to give that to you lickety-split, less than the amount of time that would take you to blink. If you run a query of arbitrary complexity, it should take no more than the amount of time that it takes to take a sip of your coffee. If you have time to get up and go make a new pot of coffee before the query returns, that's way too slow. But most importantly, we only get one shot to ingest your data. Because after that point, if we fail to ingest your data, you're going to have to drop that data in order to make room for new data. You can't afford to keep on buffering that data in RAM until it out of memories your processes. So that's how we think about our service level objectives. We think about the idea that for core ingest, we have to achieve 4 nines of reliability, or less than 4.5 minutes of full downtime if we had a full downtime incident per month. We're a little bit more lenient about the query workflows because you can always refresh the page and try again, but we only get that one shot on your telemetry. So this is what our expectation of reliability looks like and how we measure it day to day. We have, of course, another copy of Honeycomb called dog food, which measures production honeycomb, and that's how we generate these statistics. But it's all and well to measure a target, but how do we actually think about achieving it? How do we actually design to meet that 4 nines reliability guarantee? And what happens if we don't achieve it? So the DevOps research organization, Accelerate State of DevOps report, says that elite teams deploy on demand multiple times per day. And it's not necessarily that those teams are failing less often in their deploys. It's that they're recovering very, very quickly from outages. Less than an hour to deploy or to recover from a service degradation. So that's really where we've focused our energy, is how do we make it so that we cannot permanently break our system, only temporarily for a small fraction of users. So in practice, this means that we have to think about reliability throughout our entire software development lifecycle. We have to iterate and incorporate feature flag development so that in case something goes wrong, it's a matter of 5 seconds to flip off the feature flag, and we might have only impacted 1 or 2% of users rather than every user. We also invest in automatic integration and make sure that it does not get in the way of our software developers writing our own code. In particular, here's a graph of the latency involved in the build pipeline for our product. And you can see that in July and August of this year, it got a little bit slower than we would have liked, that it was reaching as high as 14 to 15 minutes. That to us was not acceptable, so we invested some time in September in making sure that we were predictably achieving a build cycle time of less than 10 minutes, so that software is not just sitting there rotting in the build queue, that it's actually getting built and shipped on a reliable schedule. And you can see that as of the past month, we're doing considerably better. We're basically bang on 10 minutes every single time, and that really makes a difference to our developer productivity, while ensuring that we're still delivering high-quality software. And speaking of delivering high-quality software, we have confidence in the combination of human code review and release testing. And the human code review is focused on that element of how are we going to observe when it's working in production, is this instrumented correctly, and the automation takes care of all of the regression testing for us. So we can be confident that anything that passes the human tests and the automated tests is safe to deploy automatically to production. And it automatically goes out within an hour or 2. So sure, we might not necessarily deploy on Friday at 6 p.m., but we definitely will deploy on Friday at 3 p.m. because we have that predictability of when things go out, and we make sure that developers are sticking around to observe the behavior in production of what they're shipping. So that's how things work with the normal software development cycle. But as we all know, things don't always go exactly according to plan. So how do we make sure that our software is meeting the safety expectations? Well, we experiment using leftover error budget, only if there's error budget left. Of course, if your service is already on fire, you should be focusing on figuring out why it is on fire and putting out those fires. But if your service is not currently on fire and has a good track record, you should always be poking at and trying to understand what might cause me to fail more than I expect in the future. So when we design chaos engineering experiments, there's usually some kind of hypothesis that we're trying to validate. What are we trying to learn from doing this experiment in production? And we make sure that there's always some kind of a safety button to press in order to make sure that we're able to restore to a known good state. So as I mentioned, feature flags can be really powerful if we're trying to test something on a small set of users. But unfortunately for us, not everything can be tested with feature flags. Because at the end of the day, Honeycomb is a big data problem where we need to persist the data and make sure that we have durability and reliability for our customers. So while the top tier of things that I'm showing on the screen, Doodle, Poodle, and Shepherd, those are all stateless services that we can deploy on demand, that we can feature flag. Everything below that on the diagram, those are all stateful services that store customer data on disk and that we can't necessarily just switch off. Or can we? So this is where it pays to understand some of the primitives of how persistence works at rest. When we ingest data into Honeycomb, it comes as a stream of events that flow into Shepherd, which is our ingest service. And Shepherd decides to send that data to one or multiple different Kafka partitions, because we utilize Kafka to provide that durability layer between stateless ingest and mostly stateful indexing, but we'll talk about that. So at the end of the day, what Kafka is giving us is this ordered stream of events. And we can go ahead and make sure that we are replaying or reading from that ordered stream of events and then performing the transformations needed to write it to S3. So a couple of things make this really challenging. Unlike our normal software development process that pushes changes every hour, we don't necessarily make a major change that would require restarting Kafka every hour. We have to think about the picture of how do we ensure data integrity and consistency for things that happen not very often, right? How often do we lose a Kafka node? If AWS is doing its job, that's not going to be very often because we're not utilizing spot instances for that. We're using on-demand instances, which are supposed to stay up. And when things do wind up degrading availability or degrading the amount of redundancy in the system, there are all kinds of delicate failover dances that are required by Kafka or by our durable storage systems that need to happen to restore that redundancy. It's not just a matter of restart the service and it comes back up. So let's suppose, for instance, that we lose one particular Kafka worker node. What is supposed to happen after that? Well, in theory, we get a brand new Kafka broker, and the existing Kafka broker should help restore the state of the partition onto that Kafka node, and we should be back at replication factor 3, ideally. Similarly, if we lose one of our indexing workers, in theory, we should be able to grab a fresh snapshot of the previous indexing worker's hard disk contents off S3 and the Kafka offset it was running from and replay that forward. So we'll go ahead and just replay the stream, which should be in the same consistent order from the same offset and get the same bytes on disk. But how do we actually verify that, right? Like all of that sounds good in theory, right? That looks great on a white paper. How do we actually make sure that it works when we need it the most? The answer for us is that we have to test those properties. We have to restart one server and one service at a time. We don't restart everything, right? Like we don't necessarily run Netflix's Chaos Monkey like on our entire fleet. But we do want to be thoughtful about making sure that we can tolerate the loss of a Kafka broker or tolerate the loss of a retriever indexing node. And we also want to control the timing of this. We want it to happen at 3 p.m., not at 3 a.m. This is for a variety of reasons. First of all, it ensures that most of our team is on deck. And when I say 3 p.m., I mean 3 p.m. in the US mostly, because that's where most of our team is based. I'm here as a safety net in case things do go wrong out of hours. But in general, we prefer for most of the team to be awake. But the other important thing is to do this during peak traffic load, right? The worst time to lose redundancy is when you're receiving the most traffic, because then you have the least bandwidth available to repopulate existing nodes. And we have to check. We have to make sure that if we replace a given Kafka node, and we're choosing to do it rather than Amazon making the decision as to when it happens, we want to make sure that there are no blips induced to our ingest pipeline. That, for instance, the shepherd nodes that are the stateless ingest workers, that they're noticing that the Kafka partition they're trying to write to has gone temporarily unavailable, and they need to make sure to redirect that traffic to a Kafka partition that is working correctly, at least until we can get that partition up and running again. And in the event something does go wrong, we have to have the observability to understand what's gone wrong and how do we make sure that that doesn't happen again the next time we do this experiment, or heaven forbid, the next time that it happens in production. So this means that we need to make sure that our telemetry is working correctly, and when we're running an experiment, if we don't see the blip that we expected, that's a sign that we're missing telemetry, right? We can't just say, oh, like nothing went wrong, therefore, we're not going to do anything, right? Like, if we do an experiment and we don't see the little crater that we expect to see, that's a problem too. And over time, we've gotten to the point where we're able to verify these fixes by repeating them over and over. So we don't just kill Kafka brokers, once in every blue moon. We actually kill one Kafka broker every Wednesday morning in Australia. We kill one indexing worker every Tuesday morning in Australia. So that enables us to verify situations like what happens if we suddenly lose an indexing worker? Did we accidentally break the bootstrap process? Or more recently, we actually found an issue where we did not have enough spare capacity in our system to tolerate the loss of a Kafka broker. That we caught it before it became something where the Kafka worker was struggling to keep up at all when it was coming back up. We caught it just at the tipping point where the restore process was taking something like 12 to 16 hours, not the 6 hours that we expected, and that was a sign that we needed to know to upscale our Kafka cluster before it became a serious problem. So by verifying these things, this helps us identify all kinds of interesting edge cases. For instance, we had a situation before we adopted Kubernetes cron jobs where we needed to run alerts that Honeycomb users were expecting to run once a minute. And it turns out that we had multiple nodes that could potentially do that. And ideally, one worker would elect itself leader, and that would be the only one to run that minute. But we tried restarting nodes from our Zookeeper cluster, and we discovered that if you restarted the 0th Zookeeper node, neither alerting worker would succeed at getting the lock, and no alerts would run. Oops. And it turns out that all of the redundancy in the world in your Zookeeper cluster does not matter if your clients that are talking to Zookeeper are not reaching the quorum of all Zookeepers and are just talking to the 0th worker. So after we fixed that bug, we were able to safely restart a Zookeeper cluster and continue to have alerts work. So by using both design and automation, we've been able to de-risk our systems and ensure that they're able to work correctly even if something chaotic happens in production, whether it be us inducing that chaos or AWS doing it for us. So for instance, we now believe that we can safely lose indexing workers, even lose an entire availability zone at a time, and actually have things restore correctly. And that continuous verification process is really important. Because if you don't test these things yourself, you're going to have those things break anyways in production. If you're using AWS spot nodes, if you're using Kubernetes, right, like Kubernetes reserves the right to reschedule your workload. There's not necessarily a guarantee that things are going to keep running on the same node forever. So by ensuring that things survive being moved around, you're giving yourself a lot more flexibility because you know your system is designed to tolerate that level of chaos. So overall, chaos testing creates stronger platforms. Rather than eroding the safety of your platforms, it's helping you discover what your safety margins of your systems are so that you then have confidence to build on top of them. But not every experiment succeeds, right? Like I talk a big game about what happens if you restart a Kafka broker, right? And our answer was, it works, no problem, right? But I would be remiss to make you think that everything is sunshine and roses. So let's talk about 3 things that went wrong. So once upon a time, we had a service, we had the ingest service only supporting ingesting JSON over HTTP. But we wanted to add support for OpenTelemetry over gRPC. So our developers, with the best intentions, said, OK, let's have a separate port to listen for gRPC requests. And let's go ahead and test that locally. Hey, it works. OK, great. Let's go ahead and roll out production. and then everything crashed. The new build started rolling out, but it was failing to health check. It was failing to start up correctly, so we're eroding the capacity in our existing auto-scaling groups as the deploy went onwards. We were able to stop the deploy in time so that we weren't having a 100% outage. What happened that we weren't aware of was that our safety mechanism for stopping releases did not stop new worker nodes that were spinning up in response to increased demand from getting the newest build rather than the current golden build that they were supposed to be running. So when traffic increased, even though we'd frozen the deploy, our system became unstable and latency shot up, and we blew our SLO. Now, the Google SRE book says you're supposed to stop all deploys and wait for your SLO to recover, but we're a startup. We don't have that luxury. So we could have said, OK, so let's not do that. We thought about delaying the launch, but it turned out that this was something that was really important. It was a partner announcement with AWS. So we instead decided to get creative, right? Like, the point of the SLO is to prevent you from violating the safety constraints multiple times to damage the trust of your users. So what we chose to do was we chose to mitigate any future impact of this feature work by using a separate worker pool and ensuring that the load balancer upstream was making the routing decision about whether to use the experimental pool or the stable pool. So the experimental pool is running gRPC, but the stable pool is running everything else, and that way we could protect our users' traffic while still enabling the gRPC experiment to succeed. Here's the second failure use case. Kafka is our main persistence layer, as I talked about, and we wanted to make sure that we were running it as efficiently as possible while preserving stability and safety. So for a long time, we've been using Confluent Kafka, and Confluent Kafka released this feature called data tiering, where you could tier older data that was less recently accessed. And our goal here was to stop running 30 or 40 different Kafka brokers and reduce the number of Kafka brokers we were running to a more manageable 6 or 9. Because it turned out that we didn't need 100% of that data to be fresh on disk. We merely needed a safety margin of something like 1 to 2 hours to be able to do our replays safely, rather than needing the full 24 hours. If we need the past 24 hours of data, that's a sign that something's gone further wrong. That can take a little bit more time to restore. It doesn't have to be sitting on local SSD. So as you can see, for a while, we were running a very high number of workers. We were running as many as, I think, 30 or 40 i3EN X large nodes. And we tried to say, OK, we're going to tier all of the older data off, and therefore we only need the amount of SSD corresponding to the number of disks, the amount of disk space that the most recent hour will take, right? But it turns out that there are 5 different dimensions in a Kafka cluster you need to care about: CPU, disk size, spindles, RAM, and network. And we kept on bumping into 2 dimensions we did not think were going to go wrong. We thought we were right-sizing disk size and CPU, but that created bottlenecks on disk speed and network. And ultimately, we decided that it was not worth trying to min-max the whole thing, that the safety of the system and the safety of our people, to have enough time to react in case something went wrong, that was more important to us than a few dollars. And it took until December of 2021, about a year ago, until we were able to actually move into our preferred configuration once Amazon released the right instance shapes to help meet the use case that we had. So we briefly went to having the previous instance generation type that we were using before, just fewer of them. And eventually, we were able to run the correct architecture, the correct size of machine that was going to meet our needs and provide adequate safety margin. So safety of your people should always take precedence when you're dealing with any kind of chaos engineering, any kind of experiments or emergencies. Finally, I want to talk about the use case of being able to make changes at your infrastructure level using feature flags. We use AWS Lambda in order to power that ability to return data in less than 10 seconds, no matter how many million files on disk you're querying. And it turns out to be our most expensive our most expensive backend service spend. But AWS had released Graviton EC2 instances powered by ARM processors, which worked great for us. We were really thrilled with them, but we wanted to migrate our Lambda usage over to Graviton as well in order to avail ourselves of better performance and lower cost. So we tried turning it on with feature flags. We said, let's just try an A/B test. Let's just try running 50% ARM, 50% x86 and see what happens, right? And it fell over. It fell over and actually made cost worse, performance worse. It made users experiencing about 1.5x latency, and it was not satisfactory. So we had to turn it off right quickly. But fortunately, because we designed things with feature flags, you'll notice the timestamp there, 6:49 p.m. At 6:49 p.m., we were able to flip it back to 1% without any problems. So having that safety made it possible for us to do this experiment, knowing that even if it failed, the impact to users would be minimal. And we were able ultimately to make forward progress to optimize the things that were potentially at risk of breakage and to solve the performance bottlenecks that were causing us to see that higher than expected latency. And today, after a few false starts, right, we had to run at 30%, and then we went up to 80%, 90%. We were like, OK, that's not quite doing what we need. We need to scale it back down. We finally got to running more than 99% ARM Lambda. We just have a 1% carve-out to make sure, to our point about maintaining safety margins, that if we have to run on x86, we can safely do so still. So that's the reason why that does not say 100%. So in summary, you don't have to pick between fast delivery and reliable delivery. It's a little bit like riding a bicycle. If you're moving fast enough, you'll be both fast and not wobbly. So think about your service level objectives through the full life cycle. Manage things using feature flags to make sure that you're minimizing the impact to users in case things do go wrong. Mitigate risk and discover what could go wrong by actually inducing those failures and verifying that it meets your assumptions. But if things do go catastrophically wrong, don't necessarily stop the presses and stop everything. Think about what can you do to move safely forward the next time. And you have to include in your error budget room for both known risks as well as unknown risks. For instance, you might have things like your SSL certificate suddenly expiring or log4j happens, right? Like things like that will happen. So discover early and often through testing, can you actually do a fleet-wide upgrade of all of your instances or all of your applications? Can you rebuild those? Because you're going to have to at some point in the future, whether you like it or not. We all have various stakeholders. You're always going to have things that push the limits of what one stakeholder or another is willing to tolerate. So that's an opportunity for us to have a conversation about what did we learn, how can we do things better, rather than resorting to blame. So having this flexibility and experimentation and freedom to replace any instance at any time, that flexibility to try out things with feature flags, that enables us to run a more agile infrastructure as well as to ship code on demand a dozen times per day. In particular, one thing I wanted to highlight is that in the past month, we've succeeded at replacing 100% of our Kubernetes nodes with Graviton 3 Kubernetes nodes. And that would not have been possible without our chaos experimentation to verify that it is safe for us to replace nodes and kind of do these rolling restarts on demand, and also to test and understand what are the limits. How hot can we run our workers to minimize the number of Kubernetes nodes that we need to run? If you're interested in learning more about how we think about building systems for observability with good observability, you can check out a copy of our book for free here, which was recently published in May by O'Reilly. And finally, I encourage you to go ahead, try this out in your infrastructure. Just make sure that you have the tools to manage that risk and iterate. You can see more resources at the QR codes on screen. And thank you very much for your attention. I look forward to taking any questions that you have.
All right. Any questions? Hands? Anyone? Yes. And keep your hands up afterwards so I can run to the next person, please.
Yeah, hi. Thank you for the talk. I'm just trying to understand, we're talking about error budgets and experimenting. How does that work in practice? At what point in your 30-day cycle do you decide we have enough budget to experiment?
Yeah, so the way that we think about when we have enough error budget to experiment versus when we don't relates to that question of, if you have an SLO, that's say, your SLO says you should be 99.9% reliable. If you're at least 99.95% reliable, e.g. you have about 50% of your error budget left or more, that's a sign that you're underutilizing that budget and you can go a little bit faster and run more experiments. If you're getting down to 10 or 20% of your error budget left at the end of the month, that's a sign of, okay, any one minor incident could blow us out of SLO. That's not so good, right? So it kind of depends upon what granularity and tools you have to see what's happening with your SLO, what's the rate of burn down, how many incidents have we had, how many more similar incidents can we tolerate before we might blow that SLO. I think the most obvious case of don't run an experiment is if your SLO is blown by a factor of 100% or 200% or more, right? You have your work cut out for you. You know what you need to be doing. Or if not, you should be figuring that out. But yeah, basically anything between 50 and 90% of error budget left over is okay, we've got plenty to experiment with. And if you have over 90% of your error budget left at the end of the month, that's honestly a sign that your SLO is misset, right? That's a sign that you are dramatically over-delivering on reliability. It's possible your target is not aggressive enough. It's possible you're measuring the wrong thing. Or it's just possible that you might need to. So this is a story from my time at Google. There's a service called Global Chubby that was basically this global lock service where people would store config in Global Chubby and expect, hey, I poke this file and it updates magically for me. And people grew to over-rely on it. So that team would actually deliberately induce a 10-minute outage of that every quarter if there had not been a 10-minute outage that quarter from other causes, just to make sure that people did not over-depend upon it. So if you have way too much error budget, deliberately break it, at least if it's an internal-facing service, that you don't have people who come to depend upon documented behavior about, oh, it's always safe to keep my config in Global Chubby. Guess what? That's not true.
Next question? Yes.
Yeah, hi. What I'm interested to find out is how do you convince business, we're going to force or we're going to make customers not get a great experience, maybe a small amount, but for them to understand the importance of doing these experiments, but there is the risk that you will impact customers.
Yeah, I think that the risk of customer impact, you can make the argument that you would much rather discover it at 3 p.m., not at 3 a.m., right? You'd much rather discover it when people are available to work on it rather than have it emerge and become a sudden emergency in the middle of the night. I think that's kind of the main way to emphasize it to stakeholders is that it's a mitigation technique to discover things before you would naturally run into them anyways. So it's kind of playing with the timing of when the failure is going to happen. So it's not that you're adding new classes of failure. It's just that you're pulling forward the window of time in which you're discovering them. I think the other thing to emphasize is users have some degree of expectations, right? You shouldn't always be experimenting on the same pool of users. Or if you are, those should be users who have deliberately opted in, right? If you have a beta channel, right? Those are the users who have said, I'm willing to tolerate a little bit more risk to see the bleeding edge features, right? So I think that's basically what it boils down to is if you have to pick a percentage of users to experiment on, right? Either pick the users who are the most adventurous or make sure you're rotating that potential impact around and exclude from your experiments, right? If you have shards that have been particularly problematic, right? Those users have seen enough pain. Don't induce more pain on them. But if you have users that have been having an abnormally high degree of user experience, I think it's okay to run your experiments against those users in order to ensure the safety of the whole system at large. So it's kind of that issue of if you don't have enough data, it can feel dangerous. That's why the first job might be to gather that baseline data on how much error budget do you have, how much have you spent, on which users, who is the safest to run experiments with, so that you can have that confidence. And even if you decide not to run an experiment after that, guess what? You've still done something super valuable, right? You now understand the happiness of your users.
Who wants to make me run around next?
I
No
can
one?
stand up on here on stage and not run around. It's fantastic.
No more questions? Yes.
I'm just having a quick question around agile principles and modeling. Agile says release small and release quick. Do you believe in that?
Yeah, I think that it's, as I said, we deploy 14 times per day, right? And one of the main problems that we have actually right now is that the hourly deploy is now constraining us. Previously, when we had a dozen software developers, it was not a problem, right? Every release contained exactly one change list. Now every release contains 3 or 4 change lists because we're batching them up every hour, and to us, that's not satisfactory. That actually was the primary motivation for us to switch away from EC2 raw VMs onto Kubernetes, was that we wanted that flexibility to be able to do deployments and have central control over them so that we could pipeline them rather than have kind of cron jobs running on each machine that were just pulling the latest golden build every hour. So we do think that kind of small incremental changes can reduce risk. But again, right, that's a thing that you have to validate. You have to actually make it safe to roll out those changes, right? If you're rolling out changes once a week or once a month, right, every deploy is going to be a potential bomb that's going to explode, right? Whereas if you're regularly doing these deploys, that's going to be good, right, in the sense that every deploy is going to be at least nominally somewhat safe. The downside is that starts to expose you to some risks of what happens if your load balancer is misconfigured and there's a problem with every time you do a deploy, 1% of your traffic gets dropped because it's sent to an instance that's shutting down, right? That causes you to have to think a little bit harder about those cases of if you have a deploy in flight, if you have servers that are in lame duck mode or shutting down and they're not properly reporting lame duck status, right? How do you make sure that those are behaving correctly, right? So it's kind of not, you're right that there is kind of some risk involved with moving faster, but I think that those are things that we can mitigate for. Did I answer your question? Great. I see a thumbs up. Cool.
Thanks, mate. Thanks for the great talk. I was wondering, there's been a lot of, I guess, discussions about feature flags, and I guess a similar problem exists with feature flags to microservices when you get beyond a point of scale, especially with multiple environments with multiple different feature flags across a stack of technology. How do you see ways of combating that in an effective manner?
Yeah, I think that feature flags are fun. This is actually I have a ringer in the audience asking the awesome questions, right? So, okay. I think, right, the set of modern technologies that are going to kind of empower the next generation of software delivery, right? We understand we should all be doing microservices here. I hope so, at least, right? But I think the next generation things we need to pay attention to are CI/CD, feature flags, observability. Those are kind of the 3 things that really, really work really well together and create a virtuous cycle, where CI/CD will help you push the code that contains your feature flags out faster. Feature flags help you kind of have the right knobs to turn on individual features at a time for specific subsets of users. But you have to have observability to do that kind of big data analytics to understand really, really quickly if you are seeing 1 or 2% errors, which users, which feature flags are most strongly correlated across which particular sets of microservices, right? So I think that, yes, feature flags introduce complexity and introduce combinatorial complexity. But observability is well positioned to be able to answer those questions about combinatorial complexity and to pull out those high cardinality and high dimensionality values to help you understand really quickly where is this coming from. Right, you're 100% correct that kind of I'm a little bit skeptical, right, of, people are like, not just, metrics, logs, traces, but, now suddenly adding events as a category of, I have to find out every time a feature flag changes. I have to find out every time, right, X or Y or Z changes in my systems, right? And it turns out that a linear timeline of events that have happened in your system can be useful for putting together a retrospective, but it's not going to give you the operational data to understand which feature flags were in effect for which users at the time that those users started experiencing failures, right? So being able to have the data and the analysis to correlate that and understand that and to surface that as a, hey, you might want to know about this, right? Like, that's kind of how we augment human understanding in order to cope with that complexity.